All right, we're good to go. Hello. Today, we're going to run through 4.4 and 4.5, and it is literally all review from last year. There is maybe a slight little smidge of new stuff in 4.4. Maybe, I don't know if it's new, it's just maybe I'm going to explain it a slightly different way than maybe you've ever heard before. But 4.5 is stoichiometry. You've done that before, a whole bunch. And I've just got some problems on our note sheet today for you to run through. And, after that, we'll give you a chance to work on your homework before we leave for the hour. So your homework topic 1 is due tonight. I gave you an opportunity last week, Thursday, to get started on that. All of the B kids that were in front of my face were working on it. I have no clue whether or not you started it, but maybe you did. I hope you maybe gave it a shot. And if you did, you'll be in decent shape for today. But, all right, without further ado, let's go through 4.4. It's on physical and chemical changes. We've already kind of discussed that a little bit this unit anyway. But what I want to take away or give you that maybe is a little different or something is this. Physical changes. When they occur, you are breaking intermolecular forces. Okay? If I have a liquid, for example, and I would like to turn that liquid into a gas, what I need to do is I need to increase its kinetic energy, aka increase the temperature. All right? And if I increase the temperature or the kinetic energy on water molecules in a liquid phase, okay, this is my liquid version, right? Liquid phase. And if I crank up the temp, at some point, their kinetic energy, the energy of their motion, becomes greater than the attractive force holding them together, the intermolecular force holding them together. And at that point in time, once the energy of their motion gets fast enough, that intermolecular force is overcome. Okay? And now they're free and they're in the gas phase, and this is my gas phase. Thanks. So,
You could pull it out on a dance or something.
I just need glow sticks and rave music and we're golden. So when you change phase, okay, when a substance changes phase, you are breaking intermolecular forces. If you're going from solid to liquid or liquid to gas, but you can totally do the reverse, right? We can have a gas condense into a liquid freeze into a solid, and all we're doing in that instance is the exact opposite of this. Instead of speeding those molecules up or heating them up to get them to move faster, we'd just be cooling them down to get them to move slower. And what happens then is now, as the energy or the motion slows down, now all of a sudden those intermolecular forces of attraction can take hold again. They form. And now the molecules are starting to stick together because of those intermolecular forces of attraction. And your gas condenses into your liquid. Okay? And if you keep cooling it down, now your liquid freezes into a solid. It becomes rigid. All right? So long story short, again, this kind of says all of that. You're more than welcome to read through it. But the takeaway is, when physical changes occur, specifically phase changes occur, which are physical changes, obviously, what you're doing is you're either breaking or creating intermolecular forces of attraction. Attractions between your molecules. All right? So, here is a picture. Okay? From left to right, as I go from solid to liquid to gas, what you're doing in order to have those phase changes occur is you would have to break some intermolecular forces. Okay? The intermolecular forces of attraction are the strongest over here, or I really should say, these atoms or molecules are moving the slopes. Their kinetic energy is the lowest of the group. When I increase the velocity or the kinetic energy of my molecules, I start to break some of the intermolecular forces to get a liquid. And when I increase it even more, they're moving even faster. I've broken even more intermolecular forces, and now my molecules or my atoms are completely separated in the gaseous phase. Okay? The bottom arrow is showing the exact opposite, right? Instead of breaking your intermolecular forces to change phase, you could totally create new intermolecular forces to change phase, and that would be condensing, freezing. Okay? We've talked about that kind of. I don't know if we've used intermolecular forces as the context, but that's what's happened. Physical change, okay, is breaking and creating intermolecular forces of attraction between molecules, hydrogen bonds, London dispersion forces, dipole-dipole forces. Those. On the opposite side, we have chemical changes. When chemical changes occur, you are breaking and creating intramolecular forces, bonds. Okay? Here's a simple reaction of burning some hydrogen gas. Hydrogen gas, oxygen gas, when you burn hydrogen, you get water. Okay? The bonds over here get broken. We break these two covalent bonds, and we break that double bond between the oxygen atoms. On the product side, these covalent bonds between oxygen and hydrogen over here get created. So, physical changes, like I just said, breaking, creating intermolecular forces. Chemical changes, breaking and creating intramolecular forces. Bonds, covalent bonds. Okay? That's kind of the takeaway from 4.4. The one other thing that I will say, because I'll say this again a whole bunch once we get to Unit 6, is when you break a chemical bond, you've got to put energy in. Okay? Breaking chemical bonds requires energy. When new chemical bonds are created, energy is released. So if you break a chemical bond, you must put energy in. When new bonds are formed, they actually release energy as a result of formation. We'll talk a whole heck of a lot about that February. Yeah, we should. Look at that foreshadow. How exciting. Now you're so pumped for February chemistry. Okay, stoichiometry. I don't think I need to teach a darn thing. I don't think. Because this is all old news. Please, try number 1. You're going to need to balance some things. I even make you write a formula in the first one. That's Unit 1 of General Chemistry. You probably want a periodic table. You probably want a calculator, unless you can do stoichiometry math in your head, which I can't do. So if you can do that, that's pretty crazy. But that's all we got for right now. Get ahead of me. I'll show you some work. And slowly but surely throughout the hour, I'll give you these answers and make sure you guys can still do this stuff. I think you can. Last hour went pretty well. They were successful. And after you finish all this, for the notes, you're welcome to work on homework topic 1, which is due tonight. So go ahead and get started on this problem right here, which I have covered up because I don't want to write everything like I wrote last hour because I'm a lazy teacher. Yeah, efficient. Yeah. It's efficient. Let's phrase it positively. All right. For number 1, I made you do a couple things, right? First thing is iron 3 oxide is Fe2O3. Remember, the Roman numeral is the charge, not the quantity. So I have a 3 plus iron with a 2 minus oxygen. In order to make that a neutral compound, that's the ratio I need. Balancing. I'm at the end here. I didn't show my work for balancing, but if you did the balancing like we taught you last year, you would have like 3 elements listed out below the arrow, and you could count on both sides. You could use a 0.5, or 3 elements, sorry, how about 2 elements? But you could use a 0.5 method on this one, right? I think you could throw a 1.5 there along the way somewhere in your balancing and then double the whole thing. You maybe you did that, maybe you didn't. Doesn't really matter. As long as you ended up here. The work. This one was not too bad, I hope. And you can read my slop. Okay. We started with grams of iron, and we were asked to solve we started with grams of iron 3 oxide, which is the product, and we were asked to solve for the moles of iron, which is the reactant. It doesn't matter which piece we start with, right? I can give you some information about the product. I can give you some information about a reactant. It doesn't matter. I can use any one of these 3 and compare to any of the other 2, right? I could ask for grams, moles, or atoms of any of these given grams, moles, or atoms of any of the others. That's what stoichiometry is. Stoichiometry is taking a quantity of a reactant or a product and comparing that to a quantity of a reactant or a product in the same chemical reaction. That's all it is. So it should look like this. My mole ratio is 4 to 2. Obviously, that can be reduced mathematically. The coefficients are 4 and 2 in the problem, so I just left them as they are, but very clear that could also be 2 and 1. And I got this. Are there any disputes? Any questions? Anything of value that I can offer you? Keep going. Keep going. Try the next one, please. And if you're watching this as a video, please pause it and try it, because I'm basically just going to stop recording and then give you the answer. All right, for number 2. There's the balance equation. We have hydrogen and nitrogen turning into ammonia. 3, 1, 2. And we're asked to go from grams of hydrogen to grams of ammonia. You'll notice that my answer is not the appropriate number of sig figs based off of what you learned last year. It really should be 4 sig figs. But for AP Chem, just use 3 for everything. I'm telling you.
Would you mark it wrong if you did?
No, I would not mark it wrong, because actually 4 is correct, if I'm being honest with you, right? Like, following the actual sig fig rules as you learned them, it literally should be 4. But the only reason I'm using 3 is to kind of reinforce the habit. Because on the AP test, the actual AP Chem test, generally speaking, the problems they give you have 3 sig figs, almost always. But even if they don't have 3 sig figs, they will accept 3 sig figs as an answer. So why fight, right? I mean, truthfully, like, if you just get in the habit of using 3 sig figs for all your answers, your life on the AP Chem test will just be easy. Because it always works. There's nothing really you need to think about with sig figs.
Wait, so was the answer 119?
0.5.
Okay, then how did I get 118.9?
Is one of your molar masses just slightly off? You sure? If you used last year's periodic table, hydrogen is 1.00. If you use the AP periodic table, hydrogen is 1.008. That might be enough to throw you off.
Maybe I did it.
Could be. Could you just flip your digit somewhere along the line or something?
Very possible. My calculator is really old, so all the buttons are sticky, so sometimes when I hit a 0, I get like a decimal, and then I hit a 2, I get a 5. Really random.
Yeah, this is my high school calculator.
From high school?
Yeah.
Nuh-uh.
Oh, yeah.
Okay, I've actually been thinking about this recently. Like, do they die? Like, have you ever had to change your battery?
Oh, a million times, yeah.
Seriously?
And sometimes it just doesn't turn out. I have to, give it a few good whacks. Yeah. Exactly.
Do you have to, like, unscrew this whole thing with the batteries then?
Well, that one's got the solar panel here. Flip it over.
Yeah, but this ain't
Right,
like
that
this.
open up there?
Like, it's solar power?
Yeah.
Out in the
The
sun.
light power, yeah.
I never knew that.
Yeah, but this is
This thing doesn't see the sunlight, but like, so is it just light?
light, yeah.
Oh, so
It's
it's
charging
charging
on that, and I'm like, I
Sorry,
don't
yeah.
sit out there and charge
You're,
it.
correct. Everyone is by the window and
Yeah, but that's so
It
confusing.
ain't working.
flip it upside down to the window.
How does light touching that
Oh,
charge it?
really want to open that up?
Kind of, but also not really.
Let's not do that today.
My head hurts.
Yeah, the how solar panels and solar cells work is really interesting and complex. Very complex stuff. And I'm not overly well versed. Oh, I'm still recording. Hey, sorry people at home. Hopefully you're not listening to us.
I charged it. Okay.
Other people were nodding behind you. It's good.
Okay.
Hello, welcome back, online people. Hopefully. Number 3. Here's the balance expression. Okay? Took a little finagling. Again, this is one where you could have used a 0.5 to get to the correct ratios. But hopefully balancing is still A-okay. What we're going from here is atoms of manganese to mass of the product. I'm being a little more vague with how I'm describing that, I guess, by not saying the actual substance, but hopefully this makes sense. We go from atoms to moles of manganese to moles of the manganese oxide, and then so on and so forth over to the grams. I got 78.0. Did you get that? Sweet. Days like this are nice, right? I hope. This is all review. You're all done. Work on your homework. One more. The last one's the most fun because it's a limiting reactant.
Okay, let me just make sure I get that right.
All right. Last one. I'll show both chunks of this. This is a limiting reactant problem, even extra fun. Our reaction, if you can't balance it, obviously we're kind of doomed with doing stoichiometry because we need the correct ratio in order to make this work out. So hopefully you got that for our balancing. The limiting reactant part, there we go, almost. You should get this. Sorry for my label being covered up over there. And with any limiting reactant problem, you're given quantities of both the reactants, in this case aluminum and hydrochloric acid. Okay? And we just solve both of these for product. Whichever one produces less product is our limiting reactant. That's the one that's going to run out. Remember how this works. We have two quantities of reactants. They react, they react, they react, they produce product until something's gone. So at this point in time, when we've produced 15.8 grams of the aluminum chloride, we have run out of hydrochloric acid. And we can no longer produce any more. We're done. So the total amount of aluminum chloride that we can produce is the lesser of the two. Questions? For the second part, you're asked to solve for the quantity of excess. All right? And when you're asked to do this, first off, I guess, the excess was aluminum, the limiting was hydrochloric acid. And when you're asked to solve for how much excess reactant you've used, you want to start your factor label problem with the limiting reactant. Okay? In theory, you could start it with like the product of how much it was able to produce. That's okay. The reason why it's not preferred, or the reason why it's not great, is because this has already been run. And if I start another factor label problem with that number, well, then I'm just going to end up rounding it twice by the time I finish that problem, or when I find the answer. So in an ideal world, I start my excess reactant problem with my limiting reactant just like this. So then, when I find my answer, that's only been rounded once, and I'm not doing like two successive rounding situations. But anyway, so I take my my limiting reactant, I solve for my excess reactant, and this is how much of the excess I actually needed or used. I needed 3.19 grams of that stuff. I had 4.046 grams of that stuff from the previous chunk, right? There it is. So I had 4.046. I used 3.19. How much left over? 0.856. How are my sig fig rules? Not great, right? I am breaking sig fig rules based on the way that you had learned them last year with this chunk right here. But, like I said earlier, it's AP Chem. Use 3. Now, if you know the correct amount, you're welcome to be appropriate with your sig figs and give me the correct amount. I will absolutely accept that answer. And maybe that's preferred. But truthfully, when you take the AP test, you need 3. If you put 3 sig figs on all your answers, you're not going to get anything marked wrong for sig figs. Unless it's specifically a question about sig figs and the answer is not 3. You know what I'm saying? So, alright, that's all I got.